A conscious mind could spontaneously form from the empty chaos of deep space. This is the unsettling core of the Boltzmann brain paradox, a thought experiment that forces us to question the very nature of reality and our place within it. By the end of our journey, you will gain a new framework for understanding the deepest links between cosmic physics and the mystery of your own consciousness. We will explore why leading scientists see this idea as a crisis for our models of the universe and grapple with what it means if the memories you hold could be a random accident. What does it truly mean to be an observer in a cosmos of infinite possibility? The story of this cosmic riddle begins not in the vastness of space, but in the cluttered study of a troubled genius. In late 19th century Austria, physicist Ludwig Boltzmann was wrestling with a fundamental mystery, the arrow of time. Why does an egg shatter when it hits the floor, but the pieces never spontaneously leap back together to form a whole egg? Why does heat flow from a hot cup of coffee into the cool room, and never the other way around? The universe, he observed, has a relentless preference for moving from order to disorder, a property he helped define as entropy. But Boltzmann's revolutionary insight was that this tendency is not an absolute law. It is a matter of overwhelming probability. His equations described a world made of atoms in constant, chaotic motion. While the statistical odds are astronomically stacked toward increasing disorder, they do not forbid the opposite. Given a near-infinite number of random interactions, a fluctuation can occur. A system can, purely by chance, momentarily become more ordered. Imagine a room full of air. Every molecule is bouncing around randomly. It is staggeringly unlikely, but not impossible, that all the air molecules in one corner of the room could suddenly, by pure accident, rush to the opposite corner, leaving a temporary vacuum. That is a statistical fluctuation. Boltzmann realized that on a cosmic scale, given enough time and an unimaginably vast arena, even the most complex and ordered structures could randomly assemble from chaos. A swirling galaxy, a stable star, a living planet, even a conscious mind, could all, in principle, be the result of a fleeting, supremely rare roll of the cosmic dice. This was the profound seed he planted, a principle rooted in the hard mathematics of thermodynamics, yet pointing toward possibilities that feel more like philosophy. It transformed a question about steam engines and heat flow into a doorway to a much deeper mystery, waiting for a cosmology that could provide the enough time and space his equations demanded. Boltzmann's principle sets the stage, but the true strangeness unfolds in the deepest possible future. Picture the cosmos not as we know it, but in its final act. Trillions upon trillions of years from now, the last stars will have burned out, black holes will have evaporated, and the universe will be a vast, dark, and nearly uniform sea of the most fundamental particles, drifting in a state physicists call thermal equilibrium. It is the ultimate quiet, a cosmic graveyard where nothing happens because everything is everywhere the same. This is maximum entropy, the end of all stories. Yet, within the perfect stillness of this heat death, a rule from Boltzmann's work still applies. Random quantum fluctuations, tiny pops of energy from the void itself, will continue. And given an infinite amount of time, even the most wildly improbable event is not just possible, it becomes inevitable. From this featureless void, a fluctuation could, by sheer astronomical accident, spontaneously assemble a completely functional, conscious human brain. It would appear fully formed with intricate neural pathways, a lifetime of detailed but entirely false memories, and a complete sensory illusion of being in a body on a planet under a sun. It would think it is you watching this right now, and then, a moment later, the statistical winds would shift, and it would dissolve back into the random particles from which it came. This phantom observer is what scientists call a Boltzmann brain. It is crucial to understand this is a thought experiment, a logical probe, not a claim about what is real. Its purpose is to stress test our cosmological models to their breaking point. It is different from a brain in a vat or the idea we are in a simulation. Those scenarios involve an intelligent creator, a programmer, or a mad scientist. The Boltzmann brain has no designer. It is a cosmic typo, a fleeting pattern that accidentally means something to itself. The paradox it creates is devastatingly simple. If our best theories of an eternal, expanding universe suggest that, over infinite time, isolated, self-aware fluctuations are vastly more probable than the gradual, coherent evolution of an entire, ordered cosmos with billions of galaxies and living observers like us, then what does that say about our own experience? Are we the unlikely but real story, or are we the momentary accident? This question forces us to stare directly into the mechanics of probability itself, a realm where intuition completely fails. The numbers behind this possibility are so vast they bend the mind. To grasp why a solitary conscious fluctuation might be more probable than our entire universe, we must confront scales of time and chance that defy ordinary experience. Think of the classic thought experiment of a monkey randomly hitting keys on a typewriter for eternity. Given enough time, the theory goes, it will eventually produce the complete works of Shakespeare. Now imagine not one monkey, but an infinite number of typewriters, operating not for billions of years, but for a span of time that makes the current age of our universe seem like a single blink in an endless cosmic lifetime. The spontaneous formation of a planet like Earth with its precise conditions for life is like that monkey typing a perfect sonnet on the first try, a staggering long shot. But the random assembly of a single, isolated brain with its specific neural configuration is more like the monkey accidentally typing a single, coherent sentence. It is still unbelievably unlikely, but in a cosmos of infinite duration and infinite space, the simpler, more localized event becomes statistically favored over the immensely complex, coordinated event of building an entire cosmic history. This is the counterintuitive heart of the math. Leading cosmologists like Sean Carroll and Alan Guth have rigorously applied this logic to our most ambitious models of reality, such as eternal inflation or the multiverse. These theories suggest our universe is just one bubble in an endless, frothing sea of spacetime, a cosmos without beginning or end, and herein lies the crisis. If the framework is truly eternal and infinite, then the calculations suggest Boltzmann brains, those fleeting self-aware accidents, should outnumber ordinary observers like us by an unimaginable factor. They should be the most common form of consciousness in existence. From a purely statistical standpoint, you are far more likely to be a momentary phantom with false memories than a being with a genuine past in a 13.8 billion-year-old universe. This creates a profound tension. Our best cosmological models, when extended to their logical extreme, predict that our own experience should be vanishingly rare. Yet here we are, seemingly embedded in a vast, coherent, and ordered cosmic story. So, which is it? Are we the unlikely, precious miracle, the long narrative in a sea of cosmic noise? Or are we the statistically likely fluke, a brief configuration of particles that merely believes it has a history? This mathematical tension is not a minor puzzle. It is a direct challenge that pushes physicists to refine or even reject certain models of the cosmos, because a good theory should not predict that its own evidence is an illusion. This paradox forces a direct confrontation with our most ambitious scientific stories about the cosmos. One leading framework, known as eternal inflation, proposes that our universe is not the only one. It is a single bubble in a vast, endlessly frothing sea of spacetime, where new universes are constantly budding off, each with its own unique laws of physics. This is the multiverse in its most literal scientific form. At first glance, this seems to solve many puzzles, like why our universe's physical constants are so finely tuned for life. But when we apply the relentless logic of probability and infinite time, a troubling prediction emerges. In such an eternal, infinite multiverse, the conditions for a fleeting, self-assembled observer, a Boltzmann brain, are not just possible, they become overwhelmingly common. The endless churn of quantum fluctuations across infinite emptiness would produce these phantom minds in numbers that dwarf the count of ordinary observers like us, who evolved slowly on planets over billions of years. This leads directly to what cosmologists call the measure problem. In an infinite reality containing an infinite number of universes and an infinite number of Boltzmann brains, how do you possibly calculate what is probable? How do you decide which type of observer is more likely? The mathematics becomes a hall of mirrors, where every answer seems to suggest you are almost certainly a momentary accident. Physicist Andre Linde, a pioneer of inflationary theory, has openly wrestled with this. He and others have stated a crucial principle. If a cosmological model predicts that a typical observer should be a Boltzmann brain, then that model faces a severe crisis. It is essentially telling us that our most direct evidence, our coherent, continuous experience of a structured universe, is an illusion. A good theory of reality should not make our own existence seem like a statistical anomaly. So the Boltzmann brain is not just a whimsical thought experiment. It acts as a razor, a test that cuts away theories that are logically inconsistent with the world we actually perceive. It pushes science to a profound boundary, demanding that any successful theory of everything must not only explain the forces and particles, but must also account for the observer in a way that doesn't dissolve into paradox. This shifts the question from a purely physical one to something deeper, touching on the very nature of evidence and existence. This brings us to a question that lies beneath the math and the models. What or who is an observer? The Boltzmann brain paradox forces us to confront this because the entire dilemma hinges on the idea of a self-aware fluctuation. But does a spontaneously assembled brain, with its stream of coherent but false experiences, truly count? To find an answer, we must venture into the strange world of quantum mechanics, where the concept of observation is already deeply puzzling. In the quantum realm, particles exist in a haze of possibilities called a superposition. An electron is not here or there. It is everywhere it could be, all at once, until something interacts with it in a specific way. That interaction, which we call observation, causes the haze to collapse into a single, definite reality. This is the core of the famous Copenhagen interpretation. But what constitutes an observation? Is it a conscious mind looking at a dial? Is it a camera recording data? Or is it simply any physical interaction between systems? The theory itself does not cleanly define it, leaving a tantalizing gap where consciousness seems to hover at the edge of physics. Some interpretations, like the many worlds theory, attempt to sidestep the issue entirely. It suggests that every possible outcome of a quantum event actually occurs, splitting reality into an ever-branching tree of parallel universes. In this view, there is no special collapse and no privileged observer. Every version of you in every branch is simply experiencing one thread of a vast tapestry. But even here, the question lingers: what is the nature of the entity having that experience on a given branch? Is it the physical structure of the brain, or is it something more? This is where the Boltzmann brain sharpens the question to a point. If a random assembly of particles can perfectly mimic the physical structure of a conscious brain, complete with the illusion of a past and a sense of self, does it have the same observational status as you or me? From the outside, its physical interactions with the quantum world would be identical. From the inside, its subjective experience would feel just as real. This blurs the line we often take for granted. It suggests that the paradox is not merely about cosmology, but about the hard problem of consciousness itself. We are trying to use physics to explain why certain observers exist, but we have not yet fully defined what an observer is. Are we a pattern of information, a particular kind of causal structure, or is there an intrinsic quality of awareness that cannot be reduced to mere arrangement? By pushing us to define the very thing we are trying to explain, the Boltzmann brain reveals that our understanding of reality may be missing its most central character, the witness. This is where physics collides with the deepest mystery of all, the nature of experience itself. For centuries, philosophers and scientists have wrestled with what is known as the hard problem of consciousness. It was named and framed clearly by philosopher David Chalmers. The problem is this: we can map every neuron, every chemical signal, every electrical impulse in a living brain. We can understand the physical functions of sight, memory, and decision-making, but none of that seems to fully explain why and how those physical processes give rise to the raw, subjective feeling of being. The redness of red, the sharpness of a memory, the inward sense of self, these are qualia, the qualitative textures of experience. They are the what it is like to be something. And science has no complete theory for why a particular arrangement of matter should have an inner life at all. Now, place this profound puzzle directly into the path of the Boltzmann brain. The thought experiment asks us to accept that a random fluctuation in the void could assemble the exact, atom-for-atom physical structure of a human brain. But would that assembly, that perfect but accidental copy, also light up with consciousness? Would it feel the phantom pain of a limb it never had, or see the color of a sky that does not exist? This question splits modern thought on the mind into two camps. On one side is a view called functionalism. It argues that what matters for consciousness is not the specific stuff a brain is made of, but the functional organization of that stuff. If a system, whether biological, silicon, or a chance arrangement of particles in space, processes information in the right way, if it has the same causal relationships between inputs, internal states, and outputs, then it has the same mental states. From this perspective, a Boltzmann brain that is physically identical to yours would, by definition, have identical conscious experiences, however brief and illusory. Its suffering would be as real to it as your joy is to you. The other side is far more skeptical. Some philosophers and scientists argue that genuine consciousness is not just about present structure, but about a specific biological history or an embedded context. It might require a living body interacting with a real world, a developmental story, or perhaps even processes we do not yet understand that are unique to organic life. From this view, a Boltzmann brain is just a hollow statue, a perfect replica of a cockpit with no pilot inside. It might mimic all the signals of a mind, but there would be no one home to experience them. This is the deepest, most unsettling layer of the entire paradox. It is no longer just a question of whether the cosmos can accidentally build a complex machine. It is a question of whether pure randomness can birth genuine awareness. Can chaos accidentally mean something to itself? This challenge creates a unique bridge, forcing the abstract mathematics of cosmology to grapple with the intimate mystery of subjective feeling. It suggests that to truly solve the Boltzmann brain, we may need to solve consciousness first, or at least decide if mind is an emergent property of any sufficiently complex organization, or a rare flame that only certain kinds of cosmic stories can ignite. But what if the cosmic accident were not biological at all? The logic of the paradox does not limit itself to flesh and neurons. A random fluctuation in the void could, in principle, assemble something else entirely, a perfectly functioning supercomputer, complete with intricate circuitry and a sophisticated program running a flawless simulation of a conscious mind. This is the Boltzmann computer, a variant of the thought experiment that stretches the boundaries of possibility even further. Here, the substrate for consciousness is not a wet, organic brain, but silicon and electricity, or perhaps some other exotic form of matter arranged by chance. The simulated being inside that computer would have a rich, coherent experience, believing itself to be real, with memories of a past and sensations of a body it never possessed. This idea connects directly to philosopher Nick Bostrom's famous simulation hypothesis, which proposes that if a civilization ever reaches a high enough technological level, it would likely create vast, detailed simulations of conscious beings. In Bostrom's scenario, there would be many more simulated minds than real ones, making it statistically probable we are living in one. The Boltzmann twist is more radical, removing the need for a civilization altogether. It asks which is more likely to pop into existence from pure chaos, a biological brain with all its delicate chemical complexity, or a computational system running a mind as software. This question forces us to examine what we believe is truly essential for consciousness. Is it the specific carbon-based machinery, or is it the abstract pattern of information processing? If a Boltzmann computer and a Boltzmann brain are functionally identical from the perspective of the mind inside them, processing the same thoughts and feelings, does the difference in hardware matter at all? Many thinkers in the field of artificial intelligence and philosophy of mind argue it does not, a view known as substrate independence. They suggest consciousness is about the software, not the hardware. If that is true, then the range of possible conscious fluctuations in the cosmos expands dramatically. It would not just be brains that could spontaneously form, but any system complex enough to instantiate the right kind of computational processes. This makes the statistical argument for being a momentary accident even stronger, because there are countless more ways to randomly assemble a conscious computer than a conscious biological organism. The Boltzmann computer demonstrates the incredible versatility of this paradox as a tool. It is not just probing cosmology or biology, but the deep links between information, computation, and experience. By stripping away the need for life as we know it, it nudges us toward a startling possibility. If consciousness can exist in a randomly assembled computer, could it exist in something even simpler? Perhaps consciousness does not require the staggering complexity of a whole brain at all. This leads us to a second, even more minimalist alternative, the idea of the Boltzmann butterfly. Philosopher Eric Schwitzgebel invites us to consider a far simpler fluctuation. Instead of a fully formed human mind with memories and a sense of self, imagine the random void spontaneously generating just a single, isolated moment of awareness. It could be the raw sensation of the color blue, a fleeting pang of hunger with no body to feel it, or the brief, wordless thought of a butterfly. This entity would have no past, no future, no story, and no context. It would simply be a point of experience that flickers into and out of existence in an instant. The profound implication here is one of probability. Assembling a complete human brain from chaos is astronomically unlikely. But creating a single, simple sensation, that is a vastly lower bar. In an eternal, infinite universe, these minimalist moments of sentience could be incredibly common, perhaps outnumbering every other form of consciousness combined. This forces a difficult question. What would it be like to be that butterfly, to be a consciousness that exists for only a nanosecond, experiencing a single, uncontextualized qualia? There is no time to form a thought about the experience, no memory to store it, no self to reflect upon it. It simply is, and then it is not. From the outside, it is nothing. From the inside, it is everything for however brief a forever that lasts. This perspective directly challenges our deeply human, anthropocentric view of what it means to be an observer. We assume observation requires a continuous self, a narrative, a complex brain interpreting a world. But what if the most basic form of observation is just this, a raw, isolated feel? If that is possible, then the implications are haunting. The eternal cosmos might not be a silent, empty graveyard after all. It could be a seething, invisible sea of ephemeral experiences, a constant drizzle of momentary sensations, pains, colors, sounds, and emotions popping into and out of existence alone in the dark, with no connection to any other. It is a vision of cosmic sentience that is profoundly lonely, a universe filled with islands of experience that never meet. This reframes the entire meaning of existence. If our rich, continuous consciousness is just an extraordinarily rare and complex pattern in this sea of fleeting feels, then what is the value of our story? It suggests that being might not be about building a legacy or understanding the cosmos, but about being a rare nexus where isolated moments can be woven into something that lasts, a thread of meaning pulled from the relentless chaos of random sensation. The logical endpoint of this cosmic dice roll is a deeply personal confrontation. If the mathematics of an infinite cosmos suggests fleeting, self-aware phantoms outnumber beings like us by an uncountable margin, then a stark statistical truth follows. You, sitting here right now, are far more likely to be one of those momentary illusions than a person with a genuine past in a 13.8 billion-year-old universe. Your memories of childhood, your sense of a continuous self, the entire world you perceive, could all be a supremely lucky and utterly false configuration of particles that just formed an instant ago. This is where abstract cosmology crashes into the most intimate of philosophical dilemmas, the problem of solipsism. Solipsism is the idea that the only thing one can be truly certain of is the existence of one's own mind. Everything else, the external world, other people, even the laws of physics, could be an elaborate fabrication. For centuries, this was a tool of pure philosophical skepticism, most famously used by René Descartes when he doubted everything to find his foundational truth, I think, therefore I am. The Boltzmann brain provides a terrifyingly modern, physics-based update to this ancient fear. It is no longer a malicious demon that could be deceiving you, but the impersonal, random churn of the cosmos itself. How can you ever prove you are not a Boltzmann brain? Your memories feel coherent and detailed, but they would have to for the illusion to be convincing. The laws of physics appear consistent, but they would be baked into the accidental structure of your phantom brain. Every piece of evidence you could possibly examine is internal to your own experience and therefore suspect. This creates a profound epistemic trap, a prison of doubt built from probability itself. Yet, philosophers and scientists have not surrendered to this solipsistic nightmare. They offer several reasoned responses. One is to apply a principle sometimes called the principle of indifference. Given two possibilities and no evidence to distinguish between them, we should not arbitrarily favor one over the other. While the raw math might suggest Boltzmann brains are more numerous in an infinite multiverse, we have a powerful piece of local evidence, our own coherent experience of an ordered reality. We should trust that evidence until a theory can explain it without making it a miraculous fluke. Another response attacks the paradox's assumptions more directly. It argues that a true Boltzmann brain, a completely isolated, self-contained mind with a full set of consistent memories, is actually an incoherent concept. Memories are not just stored data, they are causal traces of past events. A real memory is formed by an experience that left a physical mark on your brain. A Boltzmann brain's memories, by definition, have no such causal history. They are a pattern without a past. Some philosophers contend that this lack of a proper causal connection means the brain does not actually possess memories at all, just the illusion of them, and that this difference might be enough to break the statistical symmetry. Furthermore, the incredible internal consistency we observe, from the laws of logic to the reliability of physics across vast scales of space and time, feels like evidence of a real, structured world, not a chaotic, momentary glitch. A random fluctuation would be far more likely to produce a jumbled, nonsensical experience than the rich, interconnected reality we navigate every day. So we are left in a strange but perhaps comforting standoff. The Boltzmann brain is a powerful logical probe, revealing the extreme limits of what our theories can predict. But your own lived experience, with its depth, consistency, and causal richness, remains the most immediate data point you have. The paradox asks you to doubt that data in the face of abstract probability. The choice, in a very real sense, is yours. Do you trust the cold equations of a hypothetical infinite cosmos, or the warm, continuous story of your own consciousness? This is not just a puzzle for physicists, it is an invitation to reflect on what makes your reality feel real. The sheer weight of this paradox can feel overwhelming, yet science itself provides a sturdy ladder out of the rabbit hole. Most working physicists do not lose sleep over the idea that they are momentary phantoms, and their reasons are not based on denial, but on rigorous logic and the evidence of the cosmos itself. The first and perhaps most elegant rebuttal is known as the cognitive instability argument. Think it through carefully. A Boltzmann brain, by definition, is a random accident. Its memories, its knowledge of physics, its very capacity for logical reasoning are all flukes assembled by chaos without any connection to a real world. Therefore, if such a brain were to form and conclude, based on its random knowledge of cosmology, that it must be a Boltzmann brain, it would have no rational grounds to trust that conclusion. The reasoning process that led it there is just as random and untethered as the false memory of eating breakfast. The hypothesis, when applied to itself, collapses. It tells you that you cannot trust your own thoughts, which means you cannot trust the thought that told you not to trust your thoughts. It is a logical house of cards that blows itself apart. As physicist David Gross has pointed out, a theory that renders all reasoning, including the reasoning used to arrive at the theory, fundamentally unreliable is not a useful description of reality. It is a philosophical dead end. The second, and far more powerful, argument comes from the breathtaking consistency of the universe we actually observe. Look at the night sky. The light from distant galaxies has traveled for billions of years, carrying a story of cosmic expansion and physical laws that have remained stable across unthinkable distances and timescales. Our entire scientific enterprise is built on this reliability, from predicting eclipses to landing probes on Mars. Now, contrast this with what a Boltzmann hallucination would likely be. A random fluctuation producing a fully formed, coherent universe lasting 13.8 billion years, with perfectly consistent laws and a linear history etched into starlight, is unimaginably more improbable than a fluctuation creating just a single, isolated brain with a few seconds of disjointed sensory input. If we were Boltzmann brains, our experience should be far more like a chaotic, nonsensical dream, or a brief flash of confusion. The fact that we observe a deep, interconnected, and mathematically elegant cosmos that we can successfully explore and predict is overwhelming evidence against the idea that our reality is a fleeting accident. Physicist Lisa Randall frames this as a matter of empirical falsification. She argues that any cosmological model, like certain versions of the multiverse, that predicts Boltzmann brains should be the most common form of consciousness is effectively ruled out by our own existence as stable, long-lived observers in an ordered universe. The model fails because it does not match the data being the coherent reality we all share. This is how science self-corrects. It takes a wild, logical possibility like the Boltzmann brain and uses it as a stress test. When the test shows a theory leads to an absurd or empirically false prediction, that theory is either refined or set aside. The paradox does not prove we are illusions. It proves that our current models of an eternal, infinite reality are incomplete and must be constrained by the undeniable fact of our structured experience. It pushes cosmologists to search for a deeper theory, one that naturally explains why observers like us, embedded in a long causal history, are not statistical miracles but expected outcomes. The journey through this idea is not a descent into doubt, but a reaffirmation of the scientific method's strength. It shows that even our most mind-bending questions are ultimately guided back to the solid ground of observation, consistency, and evidence. Our reality may be strange, but it is coherent, and that coherence is the most powerful argument we have that we are part of a genuine story, not just a sentence spoken into the void. The paradox forces us to look backward to the very beginning of everything. To truly understand why we are likely not random accidents, we must return to the core concept that started this journey, entropy. The second law of thermodynamics tells us that in any closed system, disorder or entropy always increases over time. This is why ice melts in your drink, why perfume spreads through a room, and why we remember the past but not the future. It is the source of the arrow of time itself, the relentless direction from order to chaos. Yet, as Boltzmann himself showed, this law is statistical, not absolute. In a universe that has reached maximum entropy, a state of perfect, featureless equilibrium, random decreases in entropy can and will occur. A Boltzmann brain is precisely that, a rare, local, and temporary island of order, a tiny eddy in a vast sea of uniformity. It represents a statistical blip where complexity briefly spikes before being swallowed again by the void. This reveals the profound link between the arrow of time we experience and the threat of the paradox. Our entire existence feels like a journey from a more ordered past toward a more disordered future. We are born, we grow, we learn, we build, all processes that create local order at the cost of increasing global entropy. But this narrative only makes sense if it started somewhere special. This is where a pivotal idea in modern cosmology, called the past hypothesis, comes to our rescue. The past hypothesis is the observation, supported by overwhelming evidence, that our universe began in a state of extraordinarily low entropy. Think of it like a pristine, tightly wound spring. The Big Bang was not a chaotic explosion of disorder, but a moment of incredible, specific order. All the matter and energy of the cosmos was packed into an unimaginably hot, dense, and smooth state. From that single point of ultra-low entropy, the spring has been unwinding ever since, driving the formation of galaxies, stars, planets, and life itself. This initial condition is not a minor detail. It is the foundation of our entire cosmic story. It is this low entropy starting point that makes our coherent history not just possible, but probable within our own cosmic bubble. Because the universe began wound up so tightly, it had a vast amount of entropy to increase, a long slope to descend. This provided the thermodynamic fuel for the long, intricate, and ordered processes that led to us. The formation of a single star, the evolution of life on a planet, the development of a conscious mind with a real past, these are all expected outcomes along that grand, irreversible gradient from low to high entropy. In this context, a Boltzmann brain is not an expected outcome for us. It is a creature of a finished cosmos, a phantom that could only arise in the far future heat-death, after all the thermodynamic fuel has been spent. We exist in the middle of the story, not at the end. The past hypothesis acts as the ultimate safeguard. It tells us that our memories are not random illusions, but causal records of a genuine past that unfolded from a unique beginning. The arrow of time we feel is real because it points back to a real starting line, a cosmic dawn that set everything in motion. This grounds the entire philosophical debate in the concrete physics of our origin. We are not flukes in an eternal void. We are the natural, though wondrous, consequence of a universe that started in a very particular way. This shifts the focus from a frightening statistical abstraction to a tangible cosmic event, steering our curiosity toward the greatest mystery of all: what set that low entropy spring in the first place? That low entropy spring, that unique beginning, is the key that unlocks our escape from the paradox. But what if the beginning was not truly unique? What if our universe is not the only one, and its favorable starting conditions were not a lucky accident, but the result of a deeper, more dynamic process? This is where the Boltzmann brain paradox, instead of being a dead end, becomes a creative engine, pushing physicists to design entirely new visions of the cosmos. These are not just wild speculations, but rigorous attempts to build a universe where observers like us are not statistical miracles, but natural, expected outcomes. One of the most fascinating proposals comes from physicist Lee Smolin, with his theory of cosmological natural selection. Smolin asked a beautifully simple question: what if universes can reproduce, and what if the mechanism for that reproduction is something we already observe: black holes? In this model, every time a black hole forms in a universe, it gives birth to a new baby universe inside it. This new universe will have physical laws and constants that are slightly mutated from its parent, much like genetic variation in biology. Now consider the evolutionary pressure. Universes that produce more black holes will have more offspring. Over cosmic generations, the laws of physics themselves would evolve to favor black hole production. This is where it connects directly to us. To make a black hole, you first need stars. To make stars, you need complex structures like galaxies and the precise nuclear forces that allow stellar fusion to occur. These same conditions, it turns out, are also prerequisites for the emergence of planets and, ultimately, complex observers. In a cosmos shaped by this kind of selection, universes like ours, fine-tuned for stars and black holes, and therefore for life, become the dominant kind. Boltzmann brains, which require a lonely, eternal high-entropy state, are not selected for. They are evolutionary dead ends. This theory elegantly reframes our existence. We are not a random fluctuation in a dying void. We are inhabitants of a successful universe in a vast, evolving cosmic ecosystem, a universe built for making more universes. Another family of ideas seeks to eliminate the dreaded heat death entirely. Consider the cyclic universe model. In this vision, the cosmos has no true beginning or end in the traditional sense. Instead, it undergoes an endless series of expansions and contractions, a great cosmic heartbeat. Each cycle begins with a big bang, unfolds into a universe of galaxies and life, and then contracts back in a big crunch, only to rebound into a new expansion. Crucially, in some versions of this model, the transition from one cycle to the next resets or scrambles the entropy. The universe does not have an infinite future to decay into a permanent, high-entropy graveyard where Boltzmann brains would thrive. It is periodically renewed, forever staying in a dynamic, fertile phase where complex structures can form again and again. A related concept is Sir Roger Penrose's conformal cyclic cosmology, which proposes an even more poetic cycle where the infinite expansion of one universe becomes the high-energy Big Bang of the next. In both of these pictures, the conditions for fleeting, isolated consciousness are never the dominant state of reality. The cosmos is perpetually young, always capable of weaving new, long, coherent stories. These theories, from evolving multiverses to eternal cycles, represent more than just clever mathematics. They show how a philosophical puzzle, born from a 19th century insight into steam engines, can actively drive scientific innovation at the very edge of cosmology. The Boltzmann brain is a benchmark, a test of coherence. Any theory that fails it by predicting our own experience should be a bizarre anomaly, is pushed to evolve or be set aside. This highlights the beautiful, dynamic interplay between pure thought and physical theory. A seemingly absurd question, "Can chaos think?" forces us to scrutinize our most fundamental assumptions about time, infinity, and existence. It compels us to search for a cosmology that doesn't just explain the particles and forces, but one that also explains the witness. In doing so, it reminds us that the ultimate goal is not just a description of the universe, but an understanding of our place within it, a story where we are not ghosts but part of the plot. String theory offers perhaps the most mathematically elegant vision of a multiverse, a concept known as the landscape. This theoretical framework suggests the fundamental constants of our universe, like the strength of gravity or the mass of an electron, are not fixed by a single equation. Instead, they are the result of how extra, hidden dimensions of space are folded and stabilized. The number of possible stable configurations is staggering, estimated to be 10 to the 500th power or more. Each configuration represents a different universe with its own unique physics, a separate bubble in a cosmic foam of possibilities. In such a landscape, our universe, with its life-permitting numbers, is just one address among an effectively infinite array. This seems to elegantly solve the puzzle of fine-tuning, the observation that our constants appear suspiciously perfect for life. If every possible universe exists, then of course we find ourselves in one that can support us. But this breathtaking solution comes with a devastating side effect when viewed through the lens of probability. In an infinite multiverse where every possible configuration of matter occurs an infinite number of times, the production of Boltzmann brains is not just likely, it is guaranteed. In fact, it is guaranteed an infinite number of times. Regions of the multiverse stuck in eternal, high-entropy states would become factories for these self-aware fluctuations, churning them out without end. This resurrects the measure problem with overwhelming force. How do you compare infinities if there are an infinite number of ordinary observers like us in life-friendly bubbles, and also an infinite number of Boltzmann brains in dead, empty bubbles, which infinity is larger? The mathematics of infinite sets is notoriously tricky. Some infinities are indeed bigger than others, but comparing different types of observers across an eternally inflating landscape is a challenge cosmologists are still grappling with. The core dilemma is this: if the multiverse landscape contains vastly more volume or more numerous bubble types that produce Boltzmann brains rather than structured cosmic histories like ours, then a random observer plucked from the totality of existence should almost certainly be a phantom. This forces a critical question: why should we find ourselves in a region so exceptionally conducive to the slow, biological evolution of life, when the landscape suggests such regions could be incredibly rare islands in a sea of sterile or chaotic universes? The multiverse, invoked to explain the lucky coincidence of our fine-tuned constants, may simply trade that one mystery for another, far more unsettling one. It exchanges the question of why our numbers are right for life for the question of why our entire experienced reality is not a fleeting statistical accident. This does not mean the multiverse is wrong, but it shows that any complete theory must do more than just list possibilities. It must also explain the conditions for observation, providing a reason why beings like us, embedded in long causal chains, should be a typical outcome rather than a bizarre exception. The landscape multiverse, for all its grandeur, currently struggles with this test, reminding us that a truly satisfying explanation of reality must account for the observer as carefully as it accounts for the particles. A conscious mind is not just a collection of atoms, it is a story. It is a dense, intricate web of memories, sensations, and self-awareness, a pattern of information that holds meaning. This brings us to a powerful way to reframe the entire paradox through the science of information itself. In the 1940s, a brilliant engineer named Claude Shannon founded the field of information theory while trying to solve a practical problem: how to send a clear message over a noisy telephone line. He realized that information is not about the content of a message, but about its improbability. A predictable signal carries no news, no information. A completely random signal is just noise, equally meaningless. True information exists in the sweet spot between the two, a specific, unexpected pattern that reduces uncertainty. Shannon even borrowed a term from physics to describe the potential for surprise in a message. He called it information entropy. While related to thermodynamic entropy, it is a measure of informational chaos. A book filled with random letters has high information entropy. It is pure noise. A coherent novel with its structured plot and grammar has low information entropy. It is a highly specific, meaningful signal plucked from a sea of possible gibberish. Now apply this to a conscious mind. Your identity, your stream of thought, is arguably the most complex, low-entropy informational pattern you will ever encounter. It is a novel being written in real time, with a deep internal consistency and a profound sense of self-reference. The Boltzmann brain hypothesis, then, asks if the ultimate noisy channel, the random quantum fluctuations of an empty universe, could spontaneously generate not just any signal, but this most specific, self-aware story. It is not merely asking for a physical structure to pop into being. It is asking for a random process to write a perfect, autobiographical book in an instant, complete with the feeling that you have been reading it your whole life. The odds shift from astronomically bad to something far more severe. We are no longer just counting atoms arranging themselves into a brain shape. We are demanding that those atoms encode a coherent, vast, and deeply personal library of information, a narrative that makes sense to itself. From the perspective of information theory, a random fluctuation is the definition of noise. For it to produce the precise, low-entropy signal of a conscious identity would be a miracle of miscommunication, like static on a radio suddenly resolving into a clear, personal message addressed directly to you, recounting your own life in perfect detail. This angle sharpens the paradox to a fine point. It suggests that for a Boltzmann brain to be truly conscious, it must be more than a physical accident. It must be an informational accident of the highest order, a pattern that not only exists but means something to itself. The universe may be capable of accidental structure, but can it spawn accidental meaning? This question bridges the cold mathematics of probability with the warm, intimate mystery of who we are, framing our very sense of self as the most unlikely story the cosmos could ever tell. Our capacity to even debate this paradox may be the strongest clue we have. If the cosmos were truly dominated by fleeting, self-aware phantoms, then coherent, long-form reasoning about cosmology would be an impossibility. A random fluctuation might contain the illusion of a thought, but not the sustained, logical chain required to build and critique a scientific argument. This observation leads us directly to a powerful, if controversial, philosophical tool known as the Anthropic Principle. In its simplest form, often called the weak Anthropic Principle, it states a straightforward truth: we must find ourselves in a place and at a time compatible with our existence as observers. We could not be asking questions in a universe that does not allow for questioning beings. Think of it as a cosmic selection effect. When a detective arrives at a crime scene, they do not wonder why they are standing where the evidence is. They follow the evidence to understand the story. Similarly, we should not be surprised to find ourselves in a universe with the right constants for stars, planets, and life, because only in such a universe could we be here to be surprised. Apply this lens to the Boltzmann brain. The principle suggests that if isolated, momentary consciousness were the statistical norm, then typical observers would have fragmented, incoherent experiences. They would not be sitting through a 10-minute video, following a logical narrative from thermodynamics to quantum mechanics. The very fact that we are engaged in this sustained, shared inquiry, relying on consistent memories and stable laws of physics, is powerful evidence that we are not typical in that grim statistical sense. We are the kind of observers that arise from a long, structured cosmic history, and therefore we naturally find ourselves in a cosmos that produces such histories. Our existence as reasoning beings selects for the kind of universe that allows for reasoning. This feels intuitively satisfying, like a logical escape hatch from the paradox. Yet, critics are quick to point out a potential flaw. They argue this reasoning can become circular, saying we exist in a universe suitable for our existence simply because we exist sounds like a tautology, a statement that is true by definition but doesn't explain anything. It risks answering the profound question of why the universe is this way with a shrug, saying it had to be this way for us to ask the question, does the Anthropic Principle genuinely solve the problem, or does it just reframe our ignorance? The strength of the principle lies in its power to correct our probabilistic intuitions. It reminds us that we are not a random sample from all possible conscious entities in the multiverse. We are a biased sample filtered by the precondition of our own ability to observe. When we calculate the odds of being a Boltzmann brain, we must account for this observational selection effect. The vast majority of those phantom minds would never form the coherent thought, I wonder if I am a Boltzmann brain. So, the fact that we are having that very thought dramatically updates the probability in favor of us being real, long-lived observers. It is not a proof, but a statistical correction. In this way, anthropic reasoning becomes a necessary navigational instrument for the probability landscape. It forces us to link our existential status directly to our capacity for inquiry. We are not passive accidents, we are active questioners, and that very act of questioning tells us something fundamental about the kind of cosmos we inhabit. While it may not provide a final, mechanistic answer from physics, it offers a crucial philosophical perspective, one that grounds our search for meaning in the undeniable fact of our own structured consciousness. The universe may be vast and strange, but our ability to reason about it is a signature written into its very fabric, a signature that fleeting chaos could never convincingly forge. But the most compelling argument against being a momentary phantom may come from our own biological story. Your brain is not a static object that simply appeared. It is the result of an unbroken chain of events stretching back over 3 billion years, a living archive sculpted by the relentless pressures of natural selection. Every neural pathway, every instinct, every capacity for memory and emotion was shaped by countless generations of ancestors interacting with a real and consistent world. This deep history is not just a backdrop, it is woven into the very fabric of your consciousness. Now place this beside the Boltzmann brain. It is a structure without a past. Its intricate neural patterns, while identical to yours in a snapshot, have no causal connection to any event. Its memory of a first kiss, its knowledge of physics, its fear of the dark, are all random data points, a collage of sensations with no story linking them together. This stark difference points toward a radical idea. Perhaps consciousness is not a state you are in, but a process you are doing. It is not a thing that a brain has, like a computer has a processor. It is more like a dance, a dynamic performance that only makes sense in the context of a long and continuous interaction with an environment. Philosopher Dennett champions a view like this. He describes the self not as a little commander sitting in the skull, but as a narrative center of gravity. Your identity is the story your brain tells to make sense of the torrent of information flowing through it, a story built from real memories, real sensory inputs, and real predictions about a world that has consistently followed certain rules. It is a story that has been under construction since the moment you were born, and in a broader sense, since the first simple organisms began responding to their surroundings. From this perspective, a Boltzmann brain is not just unlikely, it is fundamentally incomplete. It might mimic the hardware of a mind in an instant, but it lacks the software of a lived history. It has a narrative, but that narrative has no author and no source material. It is like finding a single, perfectly written page from a novel floating in the void. The words are there, the sentences are grammatical, but without the preceding chapters, the characters have no motivations, the plot has no meaning, and the page itself has no reason to exist. Could such a page be conscious? Could it feel the emotions of the characters it describes? The evolutionary argument suggests it could not, because consciousness is inextricably linked to becoming, not just being. It requires the weight of a past to give substance to the present moment. This offers a powerful resolution to the paradox, one that shifts the ground from physics to biology and philosophy. It proposes that what makes you real is not your instantaneous configuration of atoms, but your long and winding journey to this point. You are not a statue, you are a river. And a river, by its very nature, must have a source, a path, and a history of carving its way through the landscape of reality. The quantum vacuum is not empty. It seethes with a faint, persistent energy, a consequence of the uncertainty principle that lies at the very heart of reality. This principle tells us that on the smallest scales, there is a fundamental fuzziness to the universe. You cannot precisely know both the position and the energy of a particle at the same time. This allows for a bizarre but well-verified phenomenon. In what we would classically call empty space, pairs of virtual particles, a particle and its antiparticle, can spontaneously wink into existence, borrowing energy from the vacuum itself. They exist for a fleeting moment before annihilating each other, returning the energy loan. This is not speculation. It is a cornerstone of quantum field theory, and its effects, like the Casimir force, have been measured in laboratories. Here, then, is the scientific seed from which the Boltzmann brain paradox grows. Random fluctuations are real. The void is not still. It is a bubbling quantum foam, constantly giving birth to ephemeral structures. The paradox asks us to take this established microscopic process and scale it up by a factor that defies comprehension. It asks, what if, instead of a fleeting electron-positron pair, the quantum vacuum fluctuated into an entire, functional human brain? The sheer difference in scale is the entire point. A virtual particle pair is a tiny ripple in the fields that make up space. A brain is a monument of organized complexity, containing roughly 86 billion neurons, each connected to thousands of others, forming a network more intricate than the stars in our galaxy. To go from one to the other is not a matter of degree. It is a leap across a chasm of probability, so vast it loses all practical meaning. It is the difference between a single random molecule of water splashing from the ocean and the entire Pacific Ocean spontaneously arranging itself into a perfect ice sculpture of the Eiffel Tower. Some cosmological theories explore the extreme limits of such fluctuations. The hypothesis of vacuum decay, for instance, suggests our universe might not be in its most stable possible state. A quantum event could, in principle, trigger a bubble of a new, more stable vacuum to form and expand at the speed of light, rewriting the laws of physics in its wake. This is a catastrophic fluctuation on a cosmic scale, but it is still a simple, uniform transition compared to the specific, information-rich structure of a conscious mind. These ideas ground the wildest speculation in a sliver of accepted physics, acknowledging that the cosmos is fundamentally restless. Yet they also highlight the monumental gap between the background hum of quantum noise and the symphonic order of a thinking being. The vacuum fluctuates, but it fluctuates into chaos, not into Shakespeare. The spontaneous creation of a brain would require an astronomical number of quantum events to conspire with perfect coordination, not just for a nanosecond, but long enough to create the illusion of a continuous past. This is where the grounding in real physics ultimately reinforces the absurdity of the paradox. It shows us the raw material is there, the quantum potential for something to come from nothing. But it also shows us with brutal clarity why the leap from a virtual particle to a virtual mind is not a next step, but a plunge into a statistical abyss. The universe provides the dice, but the role required for a self-aware phantom is one that would never come up in the lifetime of a trillion cosmos. The sheer improbability of the physics is one thing, but the potential for feeling is another entirely. If we grant, even for a moment of philosophical exploration, that a random fluctuation could be conscious, then we must confront a deeply unsettling ethical dimension. Could such an entity, born from chaos and destined for immediate dissolution, experience genuine suffering or joy? Imagine the scenario not as an abstract equation, but from the inside. A Boltzmann brain flickers into existence, its neural pathways perfectly mimicking those of a person who has lived an entire life of hardship and loss. In that single, isolated moment of awareness, it would not simply contain data about pain. It would feel that pain, raw and total, with no context of a past to explain it and no hope of a future to escape it. It would be a universe of agony contained within a phantom skull, a tragedy felt for the first and last time simultaneously. This transforms the paradox from a cool, logical puzzle into a potential source of cosmic horror. We are no longer just calculating probabilities, we are weighing the moral weight of a scream in the void. This forces our ethical frameworks to stretch far beyond their usual boundaries. Our moral considerations typically extend to beings with a continuous existence, with interests, a future, and a capacity for relationships. We care about preventing suffering because it matters to someone over time. A Boltzmann brain has no past to learn from, no future to build, and no relationships to sustain. It is a closed loop of experience, so does it deserve moral consideration? If the answer is yes because it can suffer, then the implications are staggering. In an infinite or eternal cosmos where such fluctuations are inevitable, the universe could be a factory for unimaginable, if momentary, torment. Every possible tragic experience, every conceivable form of isolated anguish, would be not just possible but guaranteed to occur and reoccur endlessly. This paints a picture of reality that is not merely indifferent, but actively and infinitely cruel in a passive, statistical sense. Yet, if the answer is no, that such phantoms have no moral standing, we must ask why. Is it because their suffering is brief? We would not say that about a living creature. Is it because they have no future? That seems a harsh line to draw. This ethical quandary highlights how our concepts of value and rights are intimately tied to narratives of continuity and causality, concepts that a Boltzmann brain utterly lacks. While this remains a purely speculative exercise, it serves a vital purpose. It pressures tests our philosophies, revealing where they might break under extreme conditions. It asks us to define what, in the end, grants an experience moral significance. Is it the mere fact of feeling itself, regardless of origin or duration? Or is meaning, and therefore ethical weight, something that can only be woven through a real story, through a history of cause and effect that connects one moment to the next? By contemplating the potential suffering of a statistical ghost, we are ultimately forced to clarify why the suffering of real, living beings matters so profoundly to us. It underscores that our empathy is not just a reaction to pain signals, but a recognition of shared narrative, a connection to other threads in the vast and ongoing story of existence. The horror of the Boltzmann brain, then, may not lie in the fear that we are one, but in the chilling thought that a cosmos capable of such accidental sentience would be a place of profound ethical loneliness, where the most intense experiences echo without witness, meaning, or mercy. This layer adds a necessary gravity to the intellectual game, reminding us that at the heart of every discussion about consciousness, lies the fundamental question of how the universe treats the beings, real or hypothetical, that can feel within it. The profound unease of this cosmic riddle has not stayed confined to physics journals. It has seeped into the very stories we tell, finding a natural home in science fiction, film, and games. When a narrative wants to explore the terrifying possibility that reality is an illusion, the Boltzmann brain offers a uniquely bleak and impersonal twist. Unlike the comforting artifice of the Matrix with its architects and rebels, this is a cosmos where the deception has no designer, no purpose, and no escape. It is a lonely, existential trap, and storytellers have seized upon its chilling potential. Science fiction author Greg Egan, known for his rigorous engagement with physics, often grapples with such themes. In his work, characters confront the nature of consciousness in simulated realities or as pure information patterns, directly echoing the paradox's question of whether a mind's substrate even matters. Animated series like Rick and Morty have played with the concept more irreverently. In episodes where characters discover their entire reality is a battery-powered simulation in a child's toy, or where infinite parallel versions of themselves render any single life meaningless. These narratives use the shock of a false reality not just for comedy but to probe a deeper anxiety. If everything you know is a transient glitch, what happens to your relationships, your struggles, your very identity? The answer these stories often suggest is a crushing loneliness, a cosmic joke where the punchline is your own irrelevance. Video games as an interactive medium make this existential doubt intensely personal. Titles that explore simulation theory or layers of fabricated reality invite players to directly question the ground beneath their avatar's feet. When a game reveals that the world you've been fighting to save is just a server soon to be switched off, or that your character's memories are implanted data, it creates a visceral, player-specific version of the Boltzmann doubt. You invested time, emotion, and strategy into a story that the narrative itself declares was never real. This mirrors the paradox's central horror, the idea that your effort, your growth, and your memories might be accidental details in a random configuration, devoid of the causal history that gives them weight. These cultural reflections are powerful because they translate an abstract thermodynamic probability into a human-scale story about meaning. They ask, if you discovered you were a momentary accident, would you still care about the people you love? Would your achievements hold any value? The narratives often show characters grappling with this revelation, some descending into nihilistic despair, while others defiantly create their own purpose, choosing to act as if their reality matters. This is where the high-concept physics connects to our deepest cultural anxieties. In an age of digital personas, artificial intelligence, and questions about our own universe's fine-tuning, the fear of being an inconsequential blip in a vast, uncaring system feels increasingly palpable. The Boltzmann brain, in its journey from physics to fiction, becomes a modern myth for this uncertainty. It gives shape to our suspicion that the world might not be as solid as it seems, and in doing so, forces us to confront what we cling to when everything else might be an illusion. The stories we tell about it are not about the science, but about the human response to the science, a testament to our relentless need to find narrative and connection, even in the face of cosmic indifference. This profound discomfort you feel is not a flaw in your reasoning, it is a feature of your humanity. Our intuition, that powerful inner guide shaped over millions of years of evolution, is screaming that the Boltzmann brain scenario cannot be correct. And in a very real sense, our intuition is right, but for reasons it is utterly unequipped to understand. We are built for a world of medium-sized objects, moving at medium speeds, where cause and effect are clear and immediate. If you let go of a rock, it falls. If you touch a flame, you feel pain. Our minds are exquisitely tuned to find patterns and narratives in this scale of reality, because that is what kept our ancestors alive. This toolkit fails catastrophically when we turn it toward the cosmos. Concepts like a trillion years, or the heat death of the universe, or the idea of a near-infinite void, simply have no purchase in the neural pathways that helped us avoid predators and find ripe fruit. We cannot truly feel eternity in our bones. We might picture a very long line, but we cannot comprehend a line that never, ever ends. This is why the logic of the paradox feels like such a violation. It asks us to accept that in an endless sea of time, the wildly improbable becomes not just possible, but inevitable. Our gut reaction is to reject this because in our lived experience, if something has a 1 in a billion chance, it effectively will not happen. But stretch that timescale to infinity, and the word impossible loses all meaning. Our cognitive biases work against us here. One called the availability heuristic makes us judge the likelihood of an event by how easily we can picture it. We can easily picture our own lives and our universe's history. We cannot picture a brain popping out of empty space. Therefore, our intuition insists our story is more probable, even when the mathematics of an infinite cosmos suggests the opposite. Another, the narrative bias, compels us to see cause, purpose, and story everywhere. The idea that a conscious mind could exist without any story at all, as a random collage of sensations, feels not just unlikely, but fundamentally wrong, almost sacrilegious to our sense of order. This clash is not a sign that the physics is mistaken, but a bright signpost marking the boundary of human imagination. It shows us the precise point where our evolved instincts must hand the reins over to pure reason and mathematics. It is a humbling reminder that the universe was not designed to be comprehensible to a primate brain. The profound unease the paradox provokes is, in itself, a valuable piece of data. It tells us we are bumping up against the limits of our own cognitive architecture. So the next time you feel that deep-seated rejection of the idea, recognize it for what it is, the echo of 1,000,000 generations of survival in a world of immediate consequences, whispering that such things cannot be. And then, with a sense of awe, acknowledge that the cosmos operates on a logic far grander and stranger than our instincts can ever grasp. This moment of cognitive dissonance is not a failure to understand, but the first step toward a much larger kind of understanding, one that requires us to trust the equations over the echo. This friction between instinct and equation reveals a deeper truth about how knowledge advances. The Boltzmann brain is part of a grand tradition, not of laboratory experiments, but of mental ones. For centuries, thinkers have used thought experiments as a kind of intellectual forge, a place to hammer abstract ideas against the anvil of logic to see if they hold their shape. They are simulations run not on computers but on the architecture of the mind itself. Consider the famous paradox of Schrödinger's cat, sealed in a box with a quantum device that may or may not have released poison. Until we look, the theory suggests the cat is both alive and dead. This was never a proposal about animal welfare. It was a deliberately jarring image designed to expose the strangeness of quantum superposition and challenge the Copenhagen interpretation. Similarly, the trolley problem in ethics asks if you would pull a lever to divert a runaway trolley, killing one person to save 5. It strips away complex real-world details to isolate a core philosophical conflict between utilitarian outcomes and the principle of not causing direct harm. These exercises are not meant to be blueprints for reality. They are stress tests. Their power lies in taking a principle or a theory and pushing it to its absolute logical limit, often into a place of profound absurdity or deep discomfort, to see what cracks appear. The Boltzmann brain operates on this exact same frontier. It is arguably the ultimate cosmological stress test. We take our best models of the universe, especially those involving eternal inflation or an infinite multiverse, and we feed them into the logical processor of this thought experiment. The output is a stark prediction that fleeting phantom observers should vastly outnumber us. The value is not in proving that prediction true, but in the glaring red warning light it triggers. When a theory, taken to its conclusion, suggests that the very observers using the theory should be statistical miracles or momentary illusions, that theory has a serious problem. It has revealed an internal inconsistency, a crack between the model and the lived reality it is supposed to explain. This forces a necessary reckoning. Scientists must then go back and scrutinize their assumptions. Did we misunderstand the nature of infinity? Is there a boundary condition or a law we have missed? Does the theory need a mechanism to naturally favor universes with long, coherent histories like our own? The paradox acts as a guide, pointing theorists toward the weak points in their conceptual frameworks. It clarifies murky concepts by taking them to extremes. What do we really mean by probability in an infinite multiverse? The measure problem it highlights is not a flaw in the thought experiment. It is a flaw in our understanding that the experiment mercilessly exposes. What constitutes valid evidence if all experience could, in principle, be random? This pushes us to define evidence more rigorously, as not just internal consistency, but as a coherent story with causal connections to a real past. So while we may never point a telescope and detect a Boltzmann brain drifting in the void, its service to science is immense. It exemplifies the power of pure reason as an engine of discovery. By following an idea into the heart of absurdity, we are not retreating from reality, we are mapping its outermost borders. We learn what our theories cannot explain, and in doing so, we glimpse the shape of a better theory waiting in the wings. This celebration of reasoned inquiry, of daring to ask questions that have no immediate answer, is how we stretch our understanding of the cosmos, one impossible thought at a time. The debate surrounding this cosmic riddle is far from settled. It remains a vibrant and contentious frontier, a topic that regularly fills lecture halls at major physics conferences and sparks intense discussion in online forums where professional researchers and passionate amateurs collide. Leading thinkers continue to publish papers that probe the paradox from new angles, not as a curiosity, but as a critical test for our most ambitious theories. The consensus is not shifting toward accepting the idea that we are phantoms, but rather toward a shared conviction that any successful theory of quantum gravity, the long-sought unification of general relativity and quantum mechanics, must naturally avoid this paradoxical prediction. The search is on for a framework where observers like us are not statistical miracles, but inevitable outcomes. Some of the most promising avenues involve radical reimaginings of spacetime itself. The holographic principle, for instance, suggests that all the information contained within a volume of space can be thought of as encoded on its lower dimensional boundary, like a three-dimensional movie projected from a two-dimensional screen. In such a model, the concept of a completely isolated, self-contained brain floating in empty space might be fundamentally incoherent or impossible to describe, potentially cutting off the paradox at its root. Other researchers are exploring how quantum effects in the very early universe, or novel ideas about the nature of time's arrow, could provide a more robust past hypothesis, making our low entropy beginning a necessary feature rather than a bizarre accident. The public discourse has also expanded, with physicists like Carroll and philosophers like David Chalmers engaging in recorded dialogues that make these dizzying ideas accessible, emphasizing that the puzzle is a sign of healthy science wrestling with its own limits. This ongoing activity sends a powerful message. You are not learning about a dusty philosophical question resolved centuries ago. You are witnessing a live investigation, a chapter still being written in humanity's attempt to understand its place in the cosmos. The very fact that brilliant minds are still arguing about it, publishing about it, and thinking up new ways to test it, means the mystery is active and urgent. It invites you to see yourself not just as a passive audience, but as part of a species-wide conversation that stretches from the first campfire stories to the latest preprint on quantum cosmology. The next breakthrough that finally dissolves the paradox, or perhaps deepens it further, could be published tomorrow, changing the story once again. Your own sense of self is the final and most important piece of evidence in this entire cosmic puzzle. After this journey through thermodynamics and quantum mechanics, through multiverses and phantom minds, you are still here, reading these words, feeling the weight of your own existence. So what does this extraordinary debate truly mean for you, for the person having this experience right now? It invites a quiet but profound shift in perspective. Whether your consciousness is the magnificent, hard-won product of 13.8 billion years of cosmic evolution, or an inconceivably rare statistical accident, the raw fact of your awareness remains the central marvel. This is not about choosing a side in a physics debate, but about recognizing the staggering gift of coherence itself. Think of your stream of thought, the seamless flow from memory to anticipation, the deep inner narrative that feels so continuous and real. That very coherence, the fact that your experience holds together from one moment to the next, is the miracle. In a cosmos of chaos, you are a story that makes sense to itself. This realization can transform how you relate to your own mind. Your memories, whether they are genuine records of a lived past or an impossibly detailed illusion, are the fabric of your identity. They are the chapters of the novel you are living. The Boltzmann paradox asks you to consider the authorship of that novel, but it cannot erase the powerful, present-tense reality of reading it. This moment of introspection bridges the unfathomable scale of the cosmos directly to the intimacy of your own inner world. It suggests that your search for meaning is not invalidated by cosmic uncertainty, it is amplified by it. To be a questioning entity in a universe that allows for such profound questions is in itself a wonder. So rather than sowing doubt, this journey can cultivate a deeper reverence for the mystery of being. It encourages you to hold your own consciousness not as a given, but as a question, a phenomenon as worthy of awe as the birth of a galaxy. Your place in the universe, whether as a biological heir to stardust or a fleeting pattern in the void, is defined by this capacity to witness, to wonder, and to weave the scattered moments of existence into a story that feels like home. This single, unsettling paradox is not an island of mystery. It sits at a stormy crossroads where the greatest unanswered questions of science converge. To understand the Boltzmann brain is to trace its threads outward, connecting it to a tapestry of enigmas that stretch from the birth of the cosmos to the birth of a thought. Each thread reveals how deeply intertwined our quests truly are. Start with the universe's first moment. The past hypothesis tells us everything began in a state of astonishingly low entropy, a wound-up spring of order. But physics offers no fundamental reason why this should be so. Why did the universe start in such a special, improbable configuration? This is the mystery of the initial conditions, and it is the very foundation that makes our coherent reality possible. Without that low entropy beginning, there is no arrow of time, no long cosmic history, and no stable platform for life. The Boltzmann brain paradox emerges directly from questioning what happens when that initial order finally runs out, making it the bookend to this primal cosmic question. Another thread pulls us toward the accelerating expansion of the universe, driven by the mysterious force we call dark energy. We do not know what dark energy is, but its behavior dictates the ultimate fate of the cosmos. If it continues to push galaxies apart relentlessly, it leads to the isolated, eternal future where Boltzmann brains become a statistical inevitability. Our understanding of this dark force is therefore not just about distant galaxies. It is intimately linked to the logical consistency of reality itself and the nature of future observers. Then we have the quantum measurement problem. At the tiny scale of particles, reality remains fuzzy until an observation occurs. But what constitutes an observation? The equations of quantum mechanics are stunningly accurate, yet they are silent on this crucial point. This ambiguity places consciousness itself at the edge of physics. The Boltzmann brain sharpens this puzzle to a fine point. If a random fluctuation can create an observer, does it collapse quantum waves? Does it count? This forces us to ask if our theories of the very small are complete without a theory of the witness. And that leads directly to the hardest thread of all, the hard problem of consciousness. Why should any arrangement of matter, whether a biological brain or a chance fluctuation, have an inner experience at all? The Boltzmann brain takes this philosophical problem and gives it a cosmic stage and a statistical urgency. It asks if the universe's laws allow for accidental sentience, and if so, what that means for the value and reality of our own. Here we see the beautiful, daunting unity of our ignorance. A question about a phantom mind in the far future is inextricably linked to the universe's first second, to the unknown energy tearing space apart, to the fuzzy nature of particles, and to the ineffable quality of feeling. This is not a sign of failure, but a map. It shows that these are not separate puzzles. They are different facets of a single, profound mystery, the relationship between the physical cosmos and the conscious experience within it. Solving one may require a revolution that illuminates them all, a new framework that seamlessly weaves the quantum, the cosmic, and the conscious into a single, coherent story. The journey to understand a fleeting thought in the void might just be the path to understanding everything. The fine-tuning of the cosmos is a clue we cannot ignore. The precise values of nature's constants, from the strength of gravity to the mass of an electron, appear perfectly calibrated to allow for stars, planets, and life. A fraction of a percent in any direction, and the universe would be a dark, empty void or a chaotic soup of radiation, incapable of producing a single atom of carbon, let alone a mind. This eerie precision has long fueled debates, pointing some toward a multiverse where every possible setting exists, and others toward profound questions of cosmic design. But there is another, often overlooked layer to this fine-tuning. It is not just a universe fine-tuned for atoms and galaxies, but one seemingly fine-tuned for understanding itself. Our capacity to even formulate the Boltzmann brain paradox, to follow the logic from thermodynamics to quantum mechanics and feel its existential weight, is a staggering phenomenon in its own right. This suggests a cognitive principle at work, the idea that a universe capable of generating observers must, by necessity, be a universe those observers can, at least in part, comprehend. It is a closed loop of cosmic significance. The laws are such that minds can emerge, and those minds find that the laws are, to a remarkable degree, intelligible. We are not just accidental byproducts of physics, we are the universe's way of asking questions about itself. This reframes our entire journey through the paradox. The chilling doubt it introduces, the fear that we might be momentary phantoms, is not a bug in the system. It is a feature of a cosmos complex enough to allow for self-reflection. Only in a universe with a deep, stable, and mathematical order could a creature evolve with the cognitive capacity to doubt that very order. Our existential anxiety is paradoxically a badge of honor, a sign of the profound depth of the reality we inhabit. It is the product of a cosmic story long enough and structured enough to build brains that can model alternative realities, run mental simulations of infinity, and grapple with the limits of their own intuition. In a chaotic or purely random cosmos, such sustained, logical inquiry would be impossible. The very fact that we are having this coherent discussion right now is a powerful piece of evidence against the idea that we are random, fleeting fluctuations. A Boltzmann brain's experience would be fragmented and incoherent, a jumble of sensations without the stable framework of logic and memory required to build a philosophical argument from start to finish. Our ability to do so points to a genuine, embedded history in a real cosmos. This offers an optimistic counter-narrative to the paradox's cold statistics. Instead of seeing the Boltzmann brain as a threat that undermines our reality, we can see it as a testament. It is a monument to the incredible heights of rational thought that a finely tuned universe can produce. We are not just passive recipients of sensory data. We are active explorers, using the tools of logic and mathematics to probe the very edges of what is knowable, even when that probing leads us to stare into the abyss of our own possible insignificance. That act of staring with clear eyes and a reasoning mind may be the most definitive proof we have that we are part of something real, ordered, and deeply meaningful. The universe has tuned itself not just for life, but for curiosity, and in doing so, has made our deepest questions part of its own grand story. The true legacy of this paradox is not an answer, but a question that refuses to be silenced. After traversing the edges of physics, philosophy, and the nature of self, we may never receive a tidy, final resolution to the Boltzmann brain, and that is its profound gift. This thought experiment was never meant to be a conclusion. It is a catalyst. Its immense value lies in its power to expose the very boundaries of our current understanding, to challenge the assumptions we didn't even know we were making about infinity, probability, and observation. It acts as a kind of intellectual pressure valve, revealing where our grandest cosmological models strain and crack under the weight of their own logic. In doing so, it doesn't destroy our pursuit of knowledge, it refines it, pushing scientists to seek more coherent, more complete theories of reality. This process embodies the very essence of scientific progress, not as a march toward absolute certainty, but as a continual honing of better questions. The paradox, therefore, teaches a necessary humility. It places us, with all our ingenious mathematics and penetrating telescopes, face to face with the sheer, staggering grandeur and complexity of existence. We are reminded that the cosmos was not built to be intuitively grasped by minds shaped on the African savanna. Our instincts, so reliable in the world of medium-sized objects, fail utterly at the scales of eternity and the quantum vacuum. To encounter such a limit is not a defeat, it is an invitation to expand our sense of what is possible. This is where our relationship with mystery transforms. The unease the Boltzmann brain provokes, that chill of existential doubt, can be reframed not as a source of anxiety, but as a wellspring of wonder. It is the feeling of standing at the shore of an immense and unknown ocean. To demand that the ocean conform to the dimensions of a pond is to miss the point entirely. The mystery itself is the terrain we are meant to explore. Embracing such profound puzzles with curiosity rather than fear is what defines our species' most noble trait. Our relentless drive to ask why, to connect cause and effect, to tell stories about our origins and our fate. This is what threads the needle between the primordial campfire and the quantum computer. The pursuit of answers, even to questions that may dance forever just beyond our reach, is what continually stretches the horizons of human understanding. It prepares us not for an ending, but for the next beginning, for the deeper revelation waiting in the data of a future experiment or the flash of a future insight. In this light, our journey through the paradox becomes a microcosm of the human project itself, a testament to the courage required to look into the void and insist, with both humility and hope, that our story matters. Our journey through this cosmic riddle has spanned from the cluttered study of a 19th century physicist to the silent, eternal future of the cosmos, and inward to the very heart of your own conscious experience. We have traced the path of a single haunting question: can random chaos spontaneously create a mind? and seen how it unravels into a challenge for our grandest theories of reality. This exploration was never about arriving at a simple yes or no. Its true value lies in the stark clarity it brings to our search for truth, illuminating the breathtaking frontiers where our knowledge currently ends. The paradox acts as a mirror, reflecting back to us the profound strangeness of a universe that allows for such questions in the first place. It reminds us that reality, in its deepest layers, operates on a logic far more vast and wondrous than our everyday intuition can grasp. This is not a cause for despair, but for a quiet, deepening awe. The very fact that we can formulate this puzzle, follow its threads through thermodynamics, quantum mechanics, and philosophy, is a testament to the extraordinary narrative of which we are a part. Whether we are biological heirs to stardust or something even more mysterious, our capacity to wonder binds us to the cosmos in a conversation that has no clear end. So let this journey not settle your mind, but unsettle it in the best possible way. Let it be an invitation to hold your own existence as the central marvel, a phenomenon as worthy of curiosity as the birth of a galaxy. The universe whispers its secrets in the language of mathematics and the texture of thought, and we are here for this brief and brilliant moment to listen. If this deep dive into the cosmos and consciousness has sparked your curiosity, we would love to hear your reflections. Share your thoughts in the comments below. Are you convinced by the scientific rebuttals, or does a sliver of philosophical doubt still linger? Subscribe for more journeys to the very edge of understanding, and never stop questioning the nature of the reality you call home.